Good day, guys. I remain Mr. Adeyeye Adelu Peter. So this afternoon, I want to continue from where I stopped the other video. Simple harmonic motion. As you can see on the board, I want to show that T, which is the period, is given by 2 pi root L over G, where L is the length of our string or the length of the rope used for simple pendulum bob, and G is the acceleration due to gravity. Now, we are going to have a pendulum bob hanging from a rigid support, like the rotor stand, for example. So this is a rigid support. And then if you have a rope attached to it, hanging on it, and then this is your pendulum bob. By the time this pendulum bob is displaced at a very small angle, if you displace it so that the bob is now around here. Now don't forget that this place is the equilibrium position. Here is the equilibrium position, which is the center C. Now the bob is being displaced to this point. Now don't forget that the length of this rope is the same as the length of this one. Now, the weight of this bob, weight of the bob is equal to what? Mg. So that the weight of the bob is going to be acting downward. This M what? Mg. Now the bob is displaced at angle what? At angle theta to the vertical. This angle theta to the vertical. And if this is the part of the motion of the bob as it goes to and fro, this is the part. Then what happens is that the bob doesn't pass through this arc directly. The bob is going to pass tangential. It's going to pass tangential. It's going to be tangential to the arc. You know what the tangent means, right? So this is a tangent to the arc. So the bob is along this path, such that if the angle displaced, the angular displacement is so small, we can also consider this arc to be a straight line. So look at this broken line I'm trying to draw now. You can consider this arc to be what? To be a straight line along here. So let me call here X. So that here is now going to be 90 degrees, so that we have a right angle triangle there. Then let me produce this length L again. Let me produce it downward. Now if you look at it very well, this one now, this line, this X is perpendicular to the rope. So there's also a tension on the rope. There's a tension on the rope. Tension T, which is upward. Okay, so the bob is moving along this path, right? Towards what? Towards the center. It's tangential to this arc. The path along which the bob moves is tangential to the arc. Now, if you are familiar with vectors, resolution of forces, we can resolve this mass, this weight, of the bob into components along this rope and along the perpendicular. That's along the perpendicular to the rope, along the path of the bob. We can resolve the mass. Now this angle theta here is going to be corresponding. This angle is corresponding to this one here. This is vertical line. This is another vertical line, because the weight is acting vertically downward. So it means here is what? Here is theta. if you have two vertical lines this way, if these two lines are vertical, you know, they are parallel to each other, and then you now have a line cut through this way, so you can call this one what? A transversal, so that if here is theta, here too is what? Is theta. So these are corresponding angles. You can ignore these lines here, all these lines here. So this one looks exactly like what I have here. So that this angle is equal to this angle. Now, did you remember in vector that, are you following, guys? You remember in vector that when a force is inclined at an angle, theta to the horizontal, for example, this horizontal and this your force, F, inclined at angle theta to the horizontal, this horizontal, then this was this vertical, this y, and this was this x. This force can be resolved to what? The horizontal to the horizontal direction and also vertical direction, which we call horizontal component Fx and vertical component Fy, because the vertical and the horizontal, they are at what? Angle 90 degrees to each other, they are perpendicular to each other, and then the force happens to pass in between them. Now, if you look at what we have here, this line tangential to this arc, let me call here A, arc AC. This arc AC now, the line that is tangential to it, and the line of the rope itself, both of them are what? They are at angle 90 degrees to each other, they are perpendicular to each other. So that makes it possible for us to be able to resolve the weight of the bulb, which is mg, along this line and along the tangent to the arc. And then when you want to do horizontal component of this one, as you can see that your horizontal, the horizontal here is what? Is going to be adjacent to theta. It's adjacent to theta. While if I complete my vertical this way, my vertical here is still y. Here is y. Complete here. Here is x. The vertical is what? Is opposite, because this is also a right angle triangle now. Okay, so if you want to find horizontal component of this force F, which is inclined to what? To theta. We want to find the components along here, along the line which make an angle with the force. Is going to be Fx because what? F plus what? Theta. Then the other line is going to be Fy equals F sine what? Sine theta. So let's transfer that knowledge here. So if I want to resolve this one now along this line, it means it's going to be cos, because this mg now is making an angle with this line. Just like F is making an angle with what? With this line. Then it means if I'm to resolve along here, what am I going to have? I'm going to have along here mg, what now? Cos theta. Then the force along here is going to be what? mg sine what? Sine theta. So that this weight now has been resolved along here and along here. Now, what is the implication of this? We are not that concerned about this. We are more concerned about this. This mg sine theta. The implication of this is that this is a restoring force. This is the force that tends to restore this bulb towards where? Towards the center of oscillation. Okay? So the restoring force, which is the force that tends to restore the bulb to the center, or to the center of oscillation, or to the equilibrium position, F equals what? mg sine what? Sine theta. So let's keep this equation. Now let's come back here. Now, if you look at this triangle very well, x can be said to be what? To be opposite. While this line L can be said to be what? To be hypotenuse. This opposite, this what? Hypotenuse. So that the relationship between x, L, and theta is sine what? Sine theta equals to opposite, which is x, over what? Hypotenuse. Over what? Over L now. Sine theta is equal to x over what? Over L. Now, if theta is so small and it is in radian, if theta is so small, very small, the angular displacement, you displace it by just slightly, so small, and is measured in what? In radians, not in degree. You will discover that sine theta is going to be approximately equal to what? Equal to theta itself. I can prove that to you. Pick your calculator, convert your calculator to radian, to rad. From mode, press mode, then from mode you will see degree, you will see radian and the rest. So put it to radian, then press sine 0.5. 0.5 is a very small angle. Sine 0.5. Sine 0.5 is what? 0.47942. Now, you know, it means theta is equal to what? 0.5 degree. That's what we use. Theta is 0.5. And then it means sine theta itself is now equal to what? 0.47942. You can see now. This one can be approximated to what? To 0.5 itself. So this is 0.5. So, and then this theta here is in what? Is in radian. So where I'm driving at is that this sine theta now, therefore sine theta is equal to what? Is equal to what? Is equal to theta itself. And then I can now rewrite this equation that theta is equal to x over what? Over L. Theta is equal to x over L. So this is where I'm driving at. So that we are converting the whole of sine theta to what? To theta. Since theta is very small and it is measured in radian, not in degree. Now, when the restoring force acts towards the center, and we also know that acceleration is towards where? Towards the center. So that this restoring force will cause this mass to what? The bulk to accelerate towards the center. What do I mean by that? I can write an equation and say the restoring force mg sine theta will give us what? M what? Ma. Mg sine theta will give us Ma. And then if that is the case, this m can cancel out. So we have g sine theta equals what? Equals a. Now let me substitute my sine theta now. G. What is sine theta? Sine theta is what? Is theta. And what is theta itself? Theta is what? X over what? Over L. Equals to what? Equals to A. G times X over L is equal to what? To A. Where G is the acceleration due to gravity, X is the displacement from the equilibrium position, L is the length of the rope that is being used, while A is the acceleration which is towards the center of oscillation. Now, but since displacement X is directly opposite to what? To acceleration A. Don't forget, when we started the video, in the first video, we said acceleration is directed towards where? Towards the center, while displacement is away from the center. So meaning both are directly opposite each other. So one is towards the center, while the other one is away from the center. So that we look at the equation the other day we say A is proportional to minus what? Minus X. So you have to introduce that minus A again. So that we now have G times minus X over L. G times minus X over L will now be equal to what? A. So that minus Gx over L equals what? Equals A. But do you remember that acceleration A equals to minus what? Omega square x. Acceleration A equals to minus omega square L. So what is the implication of this? We come back here. Minus Gx over L will now be equal to, so substitute this one now. What is A? Minus omega square x. Now this can cancel out. So we have minus G over L is equal to G over L equals to omega squared. But you also remember that omega equals to 2 pi over what? Over T. Omega equals 2 pi over T. So from there, we can substitute again by saying G over L equals to, that's 2 pi over what? Over T, this omega. Then all what? All squared. So that G over L will be equal to 2 pi squared will give me 4 pi squared out of T squared. T raised to 2. Now we are going to make T the surrogate of the formula, the period of oscillation. If we cross multiply, we have T squared G equals to 4 pi square L. Okay, so that T squared will now be equal to 4 pi square L over what? Over G. Now if we find the square root of both sides to make T the surrogate formula, square root of T squared equals square root of 4 pi square L over G. Okay? So from there, these two can cancel out the square root. So we have T equals what? What is the square root of 4? Or we can even rearrange this square root of 4 pi square, since these are perfect square, then times square root of what? L over G. Do you remember? Root A over B equals what? Root A over root B. Root A times B equals root A. Sorry, root A is root A over root B. Then root A times B is what? Root A times what? Root B. Our solved expressions. Then T will now be equal to square root of 4 pi squared, that's 2 pi, then root what? L over G. So that's the expression we are trying to arrive at. Now it doesn't end here. There's a very important formula that you can also bring up from here, because we can see the whole of, if I rearrange, although this is the formula we are looking for, if I rearrange T equals to 2 pi times root 1 over G. Let me just put it this way, 2 pi root 1 over G, or 2 pi over root G. Then put it that way, then times root what? Root L. I can treat the whole of this as what? As constant. Since pi is a constant, G is also what? A constant. So what does that mean? What it means is that T is proportional to what? To square root of L. So that if T is proportional to square root of L, and I remove the sign of proportionality, this is going to be K what? K root L, meaning the whole of this is standing for what? For K. And if I make K the surrogate formula, K is going to be equal to T over root what? Root L. And then from there I can write an expression which is going to be very useful for us with the example I want to give now. So I can also say T1 now over what? Root L1, because what this means is that period depends on what? On the length of the body undergoing simple harmonic motion. So T1 over root L1 will now be equal to what? T2 over root L2. So I'm going to give an example now. This question says, a simple pendulum, you can write down, a simple pendulum has a period of 17 seconds when the length is shortened. Sorry, there's full stop there. A simple pendulum has a period of 17 seconds. That's example now. A simple pendulum has a period of 17 seconds. Full stop. When the length is shortened by 1.5 meter, when the length is shortened by 1.5 meter, what happens? Its period is 8.5 seconds. Its period now becomes 8.5 seconds to show that there's a relationship between length and what? And period. Calculate the original length of the pendulum. Calculate the original length of the pendulum. So, how do we approach this? Very simple. Very simple. So this is what we do. We have a formula here. The first period we have, which I will call T1, solution first. So they say the string pendulum has a period of 70 seconds. So we can say T1 equals to 17 what? Seconds. 17 seconds. And you can see that there's a full stop there. You can see there's a full stop there. Now, when the length is shortened by 1.5 meter, its period, meaning its new period now, period has been affected now because the length has been what? Shortened. Its new period is now 8.5 seconds. But please, what this one implies is that we don't even know what the original length is, and that is what we have to calculate. Now, what length is shortened by 1.5 meter? The original length, the length that gave us this 17 what? Seconds, which you don't know. So it means, let's call L1 now. L, let's just call it L. In what? In meters, right? Now, when that length now, this is the length that is not being shortened, the length that gave this 70 seconds period. So when that line is shortened by 1.5 meter, so you must know how to interpret simple problem in mathematics, simple word problem. So it means L2 now, the next length now is gotten when the original length is what? Is shortened by what? 1.5 meters. So our L2 is dependent on what happened to what? To L1. So we are going to express L2 in terms of the first length. And what's the first length? Ordinary L. So we are going to have L minus what? It is shortened, meaning they remove 1.5 meter from it. So shortened by 1.5 meter. Now what's the new period? T2 now. So if L2 is this, the implication of that is that the period has what? Has decreased. This 8.5 what? Seconds. Now don't forget that we said T is proportional to the root what? Root L. That is direct proportionality. Meaning when period, or let's say when length is big, is long, very long, what happens to period? Period is going to be what? Big. When length is small, because this is direct proportionality, period will what? Will also be small. So you can see here that period is big here, but when the length is now shortened by 1.5, what happens to period? It has reduced to 8.5 seconds. So just let's start to see what we have here. T1, according to our formula, over root L1 equals T2 over root L2. What's T1? 17. What's L1? Ordinary L. What's T2? 1.5. Now we find the square of both sides to remove this square root. So this is going to be 17 square over root L all square equals 8.5 square over root L minus 1.5 all what? All square. So what is 17 square?
289.
So we have 289 over L now equals to, what is 8.5 square?
72.25.
72.25. Then over, this one takes care of this L minus 1.5. Then we cross multiply. When we cross multiply, we have 289 into L minus 1.5 is equal to 72.25 L. And then if you open bracket, you have 289 L minus 289 times 1.5.
433.5.
0.5, thank you. Equals 72.25 L. So we collect like times. This is going to be 289 L minus 72. This is having L. 0.25 L, then equals, carry this one here. That's 433.5. So let me subtract. What do we have here?
216.75.
216.75 L equals 433.5. Therefore, L is what? 433.5 over 216.75. And that's what?
2.
2 on the dot, 2 meter. You can see now it means the original length is 2 meter. So the final length, which is L2, will now be 2 minus what? Minus 1.5, because they reduce the original length by 1.5. Which is now going to give us what? 0.5. You can see how much the length is being reduced from 2 to 0.5. And that is why the period 2 was reduced by a noticeable value. Okay, so I'll be stopping this video here. It's a short video. Thank you for watching. Please like, comment, and share with your friends so that they are going to benefit. Also, don't forget to press the notification button. Subscribe. Thank you.